Today I'm excited to talk to you about some of the developments that we've been working on for the exciting new field of hybrid bonding and applications for our automated AFM platforms. So here's a brief outline of our webinar today. We're going to start off with some basic introduction to what is hybrid bonding to make sure that everybody's on the same page and just sort of give a general idea of what we're going to be talking about today. I'll do a brief overview of the process flow and some of the challenges that are faced in hybrid bonding. And then we'll talk about where does surface metrology and specifically AFM fit into this hybrid bonding process flow. After that, I'll introduce everyone to the Inline Atomic Force Profiler, or AFP, and our hybrid bonding package that comes as an option for the Insight AFP platform. From here, we'll go into some specifics about some of the applications for hybrid bonding with AFM metrology. And then we'll follow it up with some of the more novel approaches for our profilometry and large area scanning on the Insight AFP platform. And we'll follow that up with some novel applications of bevel edge metrology. After that, we'll wrap up with a brief conclusion. And as Ingo mentioned, we will be available for question and answers after that. So what is hybrid bonding? In its very simplest form, hybrid bonding is just taking two wafers and bonding them together to make an electrical connection between the chips on the wafers. And by doing so, this increases the number of devices per unit area without suffering the challenges of additional 2D scale. So there are two basic methods that are approached for hybrid bonding. The first is wafer-to-wafer bonding, which we see in the cartoon in the middle, in which two wafers are processed and then brought into close contact with each other, with the process sides facing each other, and then through some annealing and some activated surfaces, these wafers bond together. There's also die-to-wafer, or also known as chip-to-wafer hybrid bonding, in which case here, rather than the full wafers being bonded together, one wafer is singulated into known good die, and then these are then individually bonded to a carrier wafer or a bottom wafer, as it's known. And so again, so why is hybrid bonding performed? Again, this is really trying to get around the challenges that we face with the 2D scaling. I mean, there's only so small we can start to make our devices. And so hybrid bonding has really emerged over the past few years as a way to change that scaling from 2D into 3D. While this is happening, though, we're also seeing scaling at the micron scale for copper pads and the copper pad connections that we'll talk about in a few minutes. So, hybrid bonding has gotten around the 2D scaling, but is now scaling itself. The great thing is that the scales over which we're talking about are really getting to the sweet spot and the key area for atomic force microscopy and atomic force profilometry. So what are some of the basic hybrid bonding steps? Obviously, this is a very abbreviated cartoon. There are a lot of steps that happen in between each of these, but there are three basic main steps. The first is surface preparation. In this case here, the two wafers are polished back. These wafers have already been through all their front-end processing and back-end processing. To do the hybrid bonding, there are copper pads that are then embedded into the dielectric, and it is this that is polished back to be a very flat surface. Once the polishing steps have been completed, the wafers are bonded together. They are first, one wafer slipped over the other, and first is what is known as an activated cold bond between the dielectric area on the wafers. And then finally, for the copper-to-copper bonding, there's a heating or an annealing step that causes the copper to expand and grow into each other, the copper pads to grow into each other, forming the needed electrical connection. So some of the challenges with hybrid bonding, though, are pretty critical. So there's the obvious one of pad alignment. You need to make sure that the pads are aligned. But topographically, and this is where AFM comes in more, has to do with the structure and the roughnesses and the surface topography of both the copper pads and the dielectric. The first and most obvious one is if there is too much copper, the copper isn't polished away enough, or if there's not enough dishing, then during the annealing process, the copper pads will actually flow out from They're individual pads and will rub into each other, causing shorts and electrical failures. If the copper is too dished, if there's not enough, or if there's too much copper removed, sorry, these can then form voids that then where there will be no electrical connection made. And lastly, there's any kind of defectivity can obviously also impact the electrical copper-to-copper connections there as well. So how does AFM fit into solving some of these topographical challenges? So this basic cartoon here, again, there's a lot of process steps that we're glossing over here, but where AFM and AFP really fits in is after the planarization of the process wafers to doing the metrology on both the dielectric and the copper pads, and up into the point of where the wafers are then bonded together. So these typical applications would include roughnesses, so roughness of the copper pads themselves, the dielectric roughness, but also some of the local topography of the pad, such as the dishing of the pads, the interface between the pad and where the pad meets the dielectric topography itself, and then also defect review. So defect review comes into play quite a bit, especially where the small topography that can be revealed by an atomic force microscope can provide additional complementary data to other defect review techniques. I'll also be talking about some new novel techniques that are used for hybrid bonding. The first that I've abbreviated here, LAS, which stands for large area scanning, is a technique that is unique to the atomic force profiler that allows nanoscale topography, basically a scanning sample AFM over the hundreds of microns up to hundreds of millimeter scales. So you can actually scan entire die or larger if needed. And we'll discuss a little bit later about why this is so important to hybrid bonding and what makes it so unique to a hybrid bonding application. And then lastly, as I mentioned, we're going to be talking a bit about the bevel. The really interesting stuff in hybrid bonding also comes at the very edge of the wafer. Bevel edge metrology has been something that that has been done on the atomic force profiler for years, mostly in the memory sector. But it has found really renewed interest in hybrid bonding due to the critical nature of the morphology of the hybrid bonding edge. So after the metrology steps, we hand it back over to the process folks, and then there'll be the alignment, the bonding, and the annealing. So thinking about those steps that we were just talking about, the roughness, the local topography of copper pads, and looking at large scale topography, this is where the Insight AFP really fits all of these cases. We have the single nanometer scale where we'll be looking at individual copper grains, the roughness of copper, the roughness of the dielectric, even the roughness of silicon in certain cases. We come up in order of magnitude and we start looking at the tens to hundreds of micron scales. And this is where we're doing our copper bond pad metrology. And we're looking at larger areas and larger topography scales over the micron scales, up to hundreds of microns. And lastly, when we really need to understand the much larger topography, but still understand it at the nanoscale, we have the option to turn to our profilometry capability and our large area scanning capability on the Insight AFP. So the Insight AFP, we've been talking about the system here for the past few slides. So just what is it? The Insight AFP, or Atomic Force Profiler, is Bruker's flagship automated AFM product for hybrid bonding.